Okay, so let's make a start. So we were talking about the Poisson distribution at the end of last week. So just to remind you, in the main lecture notes, we're on page 61 of chapter 4. And what I'm going to do now is just a quick review of the Poisson distribution. This is just a little bit of a summary that we have of, or clarification, if you like, of some of the content that we looked at on Friday of last week. This is a new file. You can find it on this alumnus system just by, you can search the lecture notes, and this is called Poisson PDF. Okay, so let me just remind you, so what we're doing is we're looking at a probability mass function, okay? The probability mass function has a range of values 0, 1, 2, off to infinity. So it's a random variable on the non-negative integers, okay? And remember that what we said is that such a random variable has a Poisson distribution, or is said to be Poisson distributed with a parameter lambda, which is some number which is strictly positive and finite, if the probability mass function looks like that, okay? And as we commented on last week, it's used for things like modeling counts, or essentially things which can grow indefinitely, okay? So just a couple of clarifications, not very much to say, but just a couple of things to say. So this is a probability mass function. Remember that what we had shown at the end of last week's lecture, that was that the expectation of a random variable with this probability mass function is lambda, and the variance is also lambda. Okay, it's a probability mass function, just in case you wanted to know, because basically this function f of x is non-zero for every x in x. This means for all x in this set x. Okay, that's because this factor lambda to the x over x factorial, or lambda is strictly positive, x factorial is at least 1, so lambda to the x is positive, so this thing is positive. E to the minus lambda is positive, so this is a non-negative function, and it sums to 1. So as I said in last week's lecture, the reason it sums to 1 is as follows. Well, you want to show that the sum over all possible values of x, okay, is equal to 1, right? This function is defined to be 0 if x is not in this support. So that's the sum over all values of x, 0 to infinity, of this function lambda to the power x, e to the minus lambda over x factorial, okay? So, as usual, we take out the constants in the summation. So e to the minus lambda is a constant, so I put it here. And now I want to show that this is equal to, this e to the minus lambda times this thing is 1. And that's true because basically this series is just the Taylor series expansion for an exponential function e to the power lambda. So this function is by definition equal to e to the lambda, and e to the lambda times e to the minus lambda is equal to 1. Okay, so that's basically just a confirmation. So I had said that last week, so just if you want to be clear about it, that's the calculation. The distribution function, remember the CDF for the cumulative distribution function, which is the probability that x is less than or equal to x. So for any x in this set x, is basically the sum from y is 0 to x of this function here. And in general, there are very few scenarios where you could compute an analytic expression for the distribution function, but you can compute it very fast, and a computer these days can do this calculation in seconds for any x, so you don't have to worry about that too much. So just a couple of simple examples before we go back to the notes. So we can of course use the probability mass function to answer elementary questions. So the probability that x, the random variable x, takes the value 1 is just f of 1. Okay, if you like, if f of 1 minus f of 0 is just lambda e to the minus lambda. The probability x is greater than or equal to 1, that's positive, is 1 minus the probability x is equal to 0, which is 1 minus the probability that x is 0, which is f of 0 is 1 minus e to the minus lambda. Okay, so just some simple calculations to kind of add on to what we had already discussed. Okay, so let's return to the main lecture notes. So this is where we were. We finished off last week, which was to start looking at some further examples on the Poisson distribution. So that's what we're going to do. So these are all questions basically designed around this notion of the Poisson. So this first example asks the following. So you've got the average number of robberies in a day is 4 in a certain big city. And we're asked, what's the probability that 6 robberies occur in 2 days? Okay. So we make the assumption that x is a random variable, and that's the number of robberies in 2 days. Okay, that's our hypothesis. Okay, and then we assume, right? From this question, you can do there are a lot of answers you could do here actually, but we're going to assume that x is distributed as Poisson with parameter lambda, and lambda, of course, is the expected number of robberies over 2 days, and we know that's going to be 4 times the number of days, which is 2. So that's 4 times 2. So basically, in our example, what we're doing is we're making the choice to model the number of robberies over 2 days as being Poisson with parameter 8. Okay, and now to answer the question, the probability of 6 robberies in 2 days, we just want to compute the probability that x is equal to 6, which is 8 to the power 6 over 6 factorial e to the minus 8. That's apparently 0.1222. Okay, and you can easily do that. That's not a, so on a calculator, even these days, it's not a problem. Although you can do it on a computer if you really like to. Okay, another way you want to do it is you can use the table of the CDF of the Poisson distribution. So the table of the CDF of the Poisson distribution, it gives you the parameter lambda, and then for any point x, it gives you the probability that x is less than or equal to x. I don't seem to have this table. I wasn't given them, so I don't know what it is. But so basically, in this table, you would have a value which is the probability x is less than or equal to 6. And if you take away the probability x is bigger than or equal to 7, that gives you the probability x is equal to 6. And so this difference between these two numbers, which can be obtained by a table. I think using tables is very, very old-fashioned. I would never think of a situation where I would do that these days. But if you like, you could use a table and calculate this. Or, there's many statistical packages which can give you these numbers as well. Okay, example 2. So again, this is another Poisson example. So if the average number of oil tankers arriving each day at a port is known to be 10. Okay, so this gives you the value of lambda if we're going with Poisson. The facilities at the port can handle at most 15 tankers per day, and the question is, what's the probability that on a given day tankers will have to be sent away? Okay, so we're going to, of course, model the number of tankers arriving as being Poisson with parameter 10, and then we're just asked to compute the probability of this event. So x is the number of tankers arriving each day. Excuse me, and we're assuming that x is Poisson 10, as I said before. It's an assumption. You could do something else, by the way, but this is a reasonable assumption here. And now what we want to do is we want to compute the probability that x is strictly bigger than 15, okay, because we start turning away oil tankers when we hit 15. So this is, of course, the sum from x is 16 to infinity of this Poisson distribution. It's the same as computing 1 minus the probability that they're 15 or less. Okay, and so this is the sum x is 0 to 15. This one's a little bit less tedious to compute than this one. And so this value is just 1 minus, so you've got e to the minus 10 comes out, and you just compute 10 to the x over x factorial from x is 0 to 15, and you add the numbers together. And so the probability of turning around a tanker is around 0.0487. If you like, you can go to this cumulative probability table of the Poisson, right? So again, we don't have this table, but essentially it's going to be a table which gives you the probability that x is greater than or equal to 16 if lambda is 10. Okay, it's just the same number, as I said. Okay, example 3 is a little bit more interesting. Let's start with the opening of the question. So it's a can company reports the number of breakdowns per 8-hour shift on its machine-operated assembly line is assumed to be Poisson with mean 1.5. Okay, so we're now asked some questions, and let's just start with A, and we'll go back to B and C. So A asks the probability of exactly 2 breakdowns during a midnight shift. So this is straightforward. If we model x as being the number of breakdowns in an 8-hour shift, then we just have to compute the probability x is equal to 2 when x is Poisson distributed with mean 1.5, i.e. lambda is 1.5. So that's exactly what I said. The probability of exactly 2 breakdowns during the night shift is that the probability x is 2, Poisson, lambda is 1.5. So this is just calculating, substituting numbers into a formula. Okay, so that's part A. So part B, what's the probability of fewer than 2 breakdowns during the afternoon shift? So it doesn't really matter if it's night or afternoon, actually. They're all the same. It's just a matter of words, actually. So we just want to compute now, in this case, the probability that the random variable x is strictly less than 2. That's just the probability x is equal to 0 plus the probability x is equal to 1. The probability x is equal to 0 is the Poisson distribution when x is 0 and lambda is equal to 1.5. And similarly, x is 1 is when x is equal to 1 and lambda is equal to 1.5. So that's the answer. So if you add these two numbers, apparently it's 0.578. Now, the third part is a little bit more interesting. It says, what's the probability that no breakdowns occur during 3 consecutive 8-hour shifts? And we are assuming that the machine operates independently across shifts. So obviously not a very reasonable assumption, but we're going to make it. So this is more interesting. Okay. So first of all, in order to find the probability of no breakdowns during 3 8-hour shifts, first consider the probability of no breakdown, during 1 8-hour shift. So we know that under our hypothesis, x, the number of breakdowns in an 8-hour shift is Poisson with parameter 1.5. So we just compute the Poisson probability mass function at x is equal to 0 when lambda is equal to 1.5. We've already done that. Apparently it was 0.2231. Okay, so that's for one shift. Now we want to compute the probability that that occurs 3 times in a row. So there are 2 ways. Well, the most obvious answer now, in fact, we could be done. So we can just multiply this number 3 times by, you just complete 0.2231 to the power 3, and that gives you the probability that you have no breakdown in 3 shifts. If you like, you can do it this way. Okay, so now you can define a random variable y to be the number of breakdowns. Number of 8-hour shifts experiencing no breakdowns in the 3 consecutive 8-hour shifts. Okay, so this is basically going to be 3 Bernoulli trials, and they're independent and identically distributed. So basically, the first one, you have an 8-hour shift, you either have no breakdowns or you do. The second one, independently, under our assumption, you have an 8-hour shift, you have a breakdown or you do, you have a breakdown or you don't, and so on and so forth until the third one, or the third one. So in this hypothesis, this is an explanation of a binomial random variable. The number of Bernoulli trials is 3, and the probability of success, which is no breakdown in a given trial, is 0.2231. So the probability that we want is just the binomial probability distribution evaluated when y equals 3, with parameters little n is 3 and p is equal to 0.2231. And that actually is just equal to this one. It's 0.2231 to the power 3, because 3 choose 3 is 1, 1 minus 0.2231 to the power 0 is 1, so it's just this one to the power 3, as I said. Okay, so what I said before, that you could just stop with this as an answer, is equally valid to do this one. This one gives you more logic as to why, but of course the fact is that you're told that the shifts are independent, so that you just have to multiply the probabilities together. It's fairly obvious, but if you like, you can do it this way. Okay, this one, there are some issues with the wording, so I will try to explain it the best I can, but there's some words missing, I feel. So it's as follows. You can read it for yourself, but let me just tell you what it is. So you have a check on the quality of wooden doors produced by a company, and its owner requested that each door has undergoing inspection for defects before leaving the plant. So these examples become sillier and sillier, but never mind. So the plant's quality control inspector finds that on average, per square foot of door surface contains 0.5 minor flaws. Okay, it's an average, so that's okay. Subsequently, you look at 1 square foot of each door surface is examined for flaws, and the decider decides to have all doors reworked that were found to have 2 or more minor flaws. Not floors and doors. Okay, so the question is, well, initially this one is, the wording is okay actually. What is the probability that a door will fail inspection and be sent back? And then we'll talk about B afterwards. So of course, we're using the Poisson distribution, so there's no mystery what we're doing. So we assume that x is the number of floors is found in 1 square foot of a door surface. Okay, and we assume that x is Poisson lambda, and x is equal. The expected value of x is 0.5. Okay, so now the probability that so it doesn't tell you how big yes. So now the probability that you fail is that you have found at least 2 floors. So the probability you fail is the probability that x is greater than or equal to 2, which is of course 1 minus the probability that x is less than 2, which is 1 minus the probability that x is 0, minus the probability x is equal to 1. Okay, and now we know the distribution of x, it's Poisson 0.5. So the probability x is equal to 0 is e to the minus 0.5. The probability x is equal to 1 is 0.5 e to the minus 0.5 over 1. And that gives you 0.0902. Part B, what is the probability that the door will pass inspection? Well, this is true if you've done part A. It's just 1 minus the probability of part A. Right, it's just 1 minus this is 0.90908. Sorry. Very good. Oh, okay. Well, this is not the one. Okay, very good. So let's move on. This is just a short foray into the notion of using an approximation of binomial distributions in the scenario where the number of trials n is very large and the success probability p is very small, or vice versa if it's very large actually. So let me explain this slide. So this is one case where I'm not going to show you the mathematics for this. It's a theorem, I guess. But the notion is this. So you have a binomial random variable x, okay? And it has parameters n and p. So the probability mass function, as we know, is n choose x. There's a typo. There should be x, not r. Okay, so for those of you who are following the notes, that's x. P to the x times 1 minus p to the n minus x. X is in the set 0, 1, 2, up to n. Okay, and now we suppose the following. Suppose that we take the number of trials to infinity and the success probability to 0, but in such a way that lambda times np is constant. Okay. So you can take n to infinity and you can take p to 0 at the rate 1 upon n, so np is 1, okay, but n goes to infinity and p goes to 0, as an example of what this statement means, okay. So this basically means we're allowing the total number of trials to get very large and the chance of success in those trials to be very small, and they're small such that the probability of success is going to 0 at the same rate at which lambda, the number of trials is increasing. Okay, this is what this thing means. So as an example of this, again, one more time, you can take the case p is equal 1 over n. Okay, and then p 1 over n times n is 1, and p goes to 0 as n goes to infinity. Okay, so then the result is the following. So the result, actually the proof, is not so hard, but we have missed a lot of steps in our development in order to do that, but this is not a mathematics course, so it's not important. So then what this result says is that the random variable x approximately has a Poisson distribution with parameter nb. That is to say that if I consider the probability mass function of the random variable x, which is binomial, I take n to infinity, I take p to go to 0, and I ensure that np is constant. Okay, then basically, if I want to compute probabilities with my binomial, I can compute my probabilities with my Poisson, and I have a good approximation. Okay, so again, let me explain. I'll say it one more time. It's important to understand what the result means, even if we don't know why it's true. What it means is, if I have a binomial distribution, I have a large number of trials, I have a success probability which is quite small. Okay. Then, if I want to do my calculations, often doing calculations with binomials can be tedious, although that's not so much the case anymore, but it used to be the case. You can imagine that this result is very old, so over 100 years old. So this was in a time where really doing computations with large n and small p was kind of very tedious. You didn't have a computer, right? So that's a problem. So instead of doing things with the binomial, you can just do them with the Poisson, and maybe these calculations are easier than doing these ones. Okay, that's really the point of it. And it's like I say, it's a little bit of an old-fashioned result because, like I say, well, it's actually important for other things, but for us at our level, it's not particularly relevant these days because these calculations can really much be done very quickly on a computer. It's not an issue anymore. But for other results, it's important. Okay, so just put in your mind, I want to do binomial, I've got large N, small p, that might be a pain, so instead I just do the Poisson on the right-hand side. That's it. That's all you have to think about. So let's have a look at this. Just a couple of examples here. So example number 1, the probability P of an individual car having an accident is 0.0001, quite small. Now you have 1,000 cars passing through a junction during a certain period of the day. And we're asked the following: what's the probability of 2 or more accidents during that period? Okay, so let's have a think about this. So let X denote the number of accidents among the 1,000 cars. So we assume that accidents are basically independent and identically distributed Bernoulli trials. We have 1,000 cars, and the chance of an accident is 0.0001. Okay, so now what I want to do is I want to compute the probability of 2 or more accidents, right? That was it. So that's the probability X is greater than or equal to 2 is the sum X is 2 to 1,000. 1,000 choose X times 0.0001 to the X, 0.999 to the power 1,000 minus X. Okay. Well, you can compute this. I mean, this is straightforward. This is the same as 1 minus the probability X is equal to 0 minus the probability X is equal to 1. So the evaluation of these numbers used to be too difficult. So this is not a slight of my colleague. Probably when my colleague was doing his PhD or something like that, this was the case. Now you really can just put in the computer and it wouldn't be a problem, right? I mean, maybe if you made this number 10 to the minus 20 and you made this number 10 to the 20, then maybe your computer might be a bit more, maybe a bit bigger, 10 to the minus 100 and 10 to the 100, then your computer starts to struggle. But this is, you can understand that the scale of today, this is not a problem. But let's suppose that it is a problem. What you could do instead of doing this, or you could, instead of doing the complement, you could use the Poisson approximation of the binomial. So n is 1,000, p is 0.0001, so n times p is 0.1. Okay, so now what I'm going to do is, instead of computing the probabilities under my binomial distribution, I use my Poisson distribution, which is an approximation of the true probability. So if I assume now X is Poisson with lambda 0.1, and I ask the question, what's the probability that X is greater than or equal to 2? That's 1 minus the probability X is equal to 0, and I subtract the probability X is equal to 1. Okay, this is a simple calculation, and 1 minus e to the minus 0.1 minus 0.1 e to the minus 0.1 over 1. Okay, so the probability is very roughly 0.047. Okay, 0.047. Okay, now this is an easy calculation that you can do on your calculator. This one, when you do 1 minus it, yeah, it should be okay these days. But definitely, if you increase the scale of this to the order of 10 to the hundreds, then this is a calculation which is just not really sensible to work with. Okay, so you see the point. It's just approximating the binomial by the Poisson, and that's your end of your story. Yeah, this is the one, I think. Which is the one which has the strange words in it? It's one of them. Maybe it's this one. Okay. So we have a manufacturing process. And we have 2 glass items, and they're being produced. Defects or bubbles occur occasionally, rendering the piece undesirable for marketing. Okay, so if you have a defect, you can't sell it. Okay, so you know that on average, 1 in every 1,000 has a defect. And so we're asked the following, and you take 8,000 of these products, and we want the probability, we want the chance that you have 7 or less have this defect. I mean, I think defect is probably the easiest thing to interpret. Okay, so let x be the number of items with this defect or bubbles. Then under our assumption, so we can assume it, right? We're making an assumption that the number of items as such, so basically an item is either going to have a defect or it isn't, and the probability of a defect is this 1 over 1,000, I believe. Yes, 1 over 1,000. And you have 8,000 independent Bernoulli trials, okay? So this random variable is binomial 8,000.001, and so for what we want to compute is the probability 1 minus, I think, no, the probability that x is equal to 0 plus the probability x is equal to 1 plus dot 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 plus the probability x is equal to 6. That's this chance here. Now, like I say, these days this is not so bad, but if you prefer an easier life, you can also do the Poisson approximation to the binomial. So if you do lambda is equal to n times p, okay, then that gives us 8. So approximately, but not exactly, x is exactly distributed as this, but an approximation of its distribution is x is Poisson lambda with parameter lambda equal to 8. Okay, so now the probability that x is less than 7 is 1 minus the probability x is greater than or equal to 7, and that's apparently 0.6866. So that's you can get that from a binomial table. This one you can compute. You can compute the probability x is 0 plus dot 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 plus the probability x is equal to 6 very fast on a calculator if you had to, and that would give you the required probability. Okay, you can use these tables as well, but that's not important. An important remark is the following: is that here we have assumed n is large and p is small, but this construction also works if n is large and p is close to 1, because then you just switch the interpretation of the Bernoulli trial. So the Bernoulli trial, you have a success or a failure. Okay, and if we interpret the chance of a success p to be extremely large, we change our interpretation that what is currently a success becomes a failure. Then the chance of a failure is exceptionally small, and we can still apply the same principle. Okay, this is what this remark means. Very good. Okay, and that's our last example in this part of the lecture notes on special probability mass functions. So let's spend some time looking at continuous distributions. So we're going to look at two examples today, which is the uniform and the exponential, and I have some additional notes for those of you who want to read ahead or stop listening to me. I'm going to talk about this file here. It's ex_example. It's on this lambda, so if you want to read that beforehand, it gives you some examples for the exponential distribution. I'm going to start with this part actually, but we haven't got there yet. So now what we're going to do is, as we did for the case of discrete random variables, we looked at special known probability distributions, the binomial, the negative binomial, the geometric, so on and so forth. And now what we're going to do is to look at the case where the random variable x can be continuous, and we start with the most basic example where the random variable x has a bounded domain. So we suppose that a random variable x is said to have a uniform distribution on an interval a,b. Okay, so a is strictly positive. A is strictly is bigger than minus infinity, less than infinity, and b is strictly bigger than a. Okay, so this is an interval, so some interval on unbounded interval. And we made this notation UAB, so a is the lower limit of the random variable, b is the upper limit, and we use u for uniform. If it's PDF, probability density function is 1 over b minus a if x is in this interval and 0 otherwise. Okay, so it's very simple. Basically, if you look at this as an example of the PDF of, I don't know why he's drawn it like this, but anyway, this is a PDF of a uniform random variable. I guess it's between 3 and 7. Uniform 3 and 7. So the PDF is basically 1 over 4 here. Okay, and then this is a discontinuity actually, so it's a discontinuity. So it's basically like this. So you basically the density, the probability of being in this region here and this region here, if the width on the x-axis is the same. So you're equally likely, essentially you can interpret it as being equally likely to be anywhere on the interval 3, 7. Okay, another thing is it's not really rectangular. I mean, normally in mathematics we don't draw this line because it's a big discontinuity. But anyway, So it's just a PDF, which is just a constant block. That's it. Okay. In fact, I'm pretty sure we've seen a PDF like that before. So we have the following. So here we will do some calculations to compute the mean and the variance. So the mean is pretty straightforward, as you might expect, right? If you think of it intuitively, I'm equally likely to lie anywhere on the interval, then on average I should lie in the middle, right? You would think that that's very roughly what you should get. And that's exactly what this result says, is that the expected value of a expected value of a uniform random variable on the interval AB has average value A plus B over 2, which is the midpoint of the interval A and AB. And the variance is a quadratic in the difference between B minus A, so it's B minus A squared over 12. Okay, and we're going to establish these two results. These are fairly straightforward, except for some small tricks with polynomials. It's pretty straightforward. Okay, so how to show the first one, the expectation of x. So remember that the expectation of a random variable x is simply x times the PDF integrated over the range of the random variable, or the support. Now the random variable in this case goes between a and b. Okay, excuse me, a and b. X is x, and this is the PDF, it's just 1 over b minus a. Okay, so to compute the expectation, I just had to calculate this integral. It's fairly straightforward because 1 over b minus a is a constant in x, so I can take it outside the integral, and I'm left with integrating the function x with respect to x, which is x squared over 2, and the limits are b and a. So the integral value is 1 over b minus a times b squared minus a squared over 2. Okay, and we know that b squared minus a squared is b minus a multiplied by b plus a. So b minus a will cancel, and you get b plus a, or a plus b, over 2 as the average value of this uniform random variable. Very good. Now to compute the variance, it's almost the same trick. There's a small algebraic trick here, which I'm going to basically gloss over a little bit, but you'll understand the point. So in order to get the variance is the expectation of the square of the random variable minus the expectation of the random variable all squared. So let's find the expected value of the square of the random variable. So by definition, that is equal to the integral over the range of support of the random variable, a to b, of the function x squared multiplied by the PDF, which is 1 over b minus a, and now I'm integrating with respect to x. Okay, so the integral here is not an issue. 1 over b minus a comes out the integral, and I want to integrate x squared with respect to x, which is x cubed to the 3, x to the 3 over 3, and I go between the limits a and b. Okay, so this is straightforward. I get 1 over b minus a, I get b to the power 3 minus a to the power 3. Okay, now you can check that b to the 3 minus a to the 3 over b minus a, it's equal to this. Okay, you can check this. It's a simple, you can do if you want, you can do this special trick with polynomials where you kind of divide through by b minus a, and you'll get this. But the easiest thing to do is if you do b minus a multiplied by this, you're going to get b to the 3 minus a to the 3. But the way to constructively show that this thing over this thing is this is to do the division of polynomials trick, which is a long time. I haven't done that since I was 19, so I really have forgotten it, so that you can just check that this one times this one is this. Okay, so the variance of the random variable x is the square of the expectation of the square minus the expectation all square. This is the expectation of the square. That's what we just computed. This is the square of the expectation. Okay, and then they were just doing simple algebra. So if you just do the simple algebra, you'll get 1 over 12 a square minus 2ab plus b square, which is b minus a all square over 12. Okay, this is algebra. I think it should be too difficult. Okay, so let's have a look. So we'll just have a look at some simple examples. Example number 1. So suppose a point is chosen at random on line segment 0, 2. Okay, what's the probability that the chosen point lies between 1 and 3 over 2? Okay, so the interpretation of this sentence, the first bullet point, is that the random if you introduce a random variable x, which is the position of the point chosen, it's basically uniformly distributed on 0, 2. And this is the interpretation that I want to compute the integral between 1 and 3 over 2 of the PDF. Okay, so x is the distribution of the position of the point, and as I said, it's uniformly distributed 0, 2. That is to say that the PDF is 1 over 2 minus 0, 2, and x lies in the closed interval 0 to 2. Okay, that's the PDF, and 0 otherwise. So now what we want to do is you're going to compute the probability that x lies between 1 and 3 over 2. So again, you don't really need to do integration here. This is just the volume of a rectangle. So the integral between 1 and 3 over 2, 1 over 2 dx, which is 1 over 2x, 3 over 2 minus 1. So that's a half times a half, which is a quarter. Okay, so that you could have worked that out without doing any probability theory. But that's the answer to the question. Example 2. Let's find the CDF. So remember the cumulative distribution function. So the cumulative distribution function of a uniformly random variable x between a and b. So remember that by definition, the CDF of a random variable x is equal to the integral between minus infinity and little x of the density function integrated with respect to t. And so remember, this t and this x must differ. You can't integrate with respect to x and have x in the limit. Okay, so how do we compute the CDF? So remember the CDF. Now, what do we have to do? What we have to do here is we have to be careful what the value of x is. So if the value of little x is strictly less than a, or less than or equal to a, basically the integral between minus infinity and x is 0 because the PDF is 0 there. Okay. If x lies between the interval a and b, then we go the integral between minus infinity and a. So we have to add this probability on, which is 0, plus the integral between a and x, 1 over b minus a dt. Okay, because the PDF is only non-zero between a and b. X is between a and b, so I integrate between a and x, and I get the density function. Now the probability that if x is less than b, well, yeah, somehow you don't have to do anything here because if x is bigger than b, you don't have to do anything now because you know the probability that x is less than or equal to b is 1. But if you like, it's the probability that I'm less than a plus the probability I'm between a and b plus the probability that I'm between b and x. Okay, but this number is 1, you know from the beginning, so this whole thing is 1. So this one's 0, this one's 1, and the only challenge is to calculate this thing, which is straightforward. Okay, so this integral here is just going to be t between a and x, so that's just going to be x minus a over b minus a. Okay, and that's basically the CDF. So it really depends on where the value of x is. So particularly you really only want to compute the CDF for x in this interval a and b, otherwise you don't care. Because you know if x is less than a, the probability of being less than a is 0. And if x is bigger than b, the probability of being less than or equal to b is 1. Okay, so that's this statement here and this statement here. And otherwise the probability of being less than or equal to x has this functional form here. Okay, very good. So let's have a look. So we're going to introduce to you this notion of the exponential distribution. I might finish a little bit early today because I want to talk about the exponential here, but don't worry, we've got plenty of material because I also want to spend some time on this sheet here, which might take a while. Okay, so the exponential density function and distribution is a continuous random variable x. And the random variable x is strictly non-negative, or positive if you like, but non-negative, the point 0 is not important. So a continuous random variable x, which is non-negative, is said to have an exponential distribution with parameter alpha. Okay, alpha is strictly positive. It's got to be finite. Okay, you can't have an infinite parameter alpha. It doesn't make sense. If it's PDF, probability density function has this form. So it's alpha e to the minus alpha x if x is positive or non-negative and 0 otherwise. Okay, and it integrates to 1. Okay, why does it integrate to 1? Well, the reason it integrates to 1 is because, of course, the integral, if I want to integrate this function, okay, we can do that. The integral of this function here, I'm trying to highlight it, is minus e to the minus alpha x. Okay, minus 1 times e to the minus alpha x. Between the integral, then if I evaluate that to infinity, I get 0, and I subtract minus 1, which is the value of this integral when x is equal to minus 1, I get back 1. Okay, so this is a nice function, easy to integrate. So that's why it's equal to 1. Okay, so before we take our break, we have a result. I actually don't like the way the result's proved, so I'm going to do it a different way in a moment. But the result is this. So if x is a random variable, which is continuous, it's non-negative. So just to say, I didn't spend any time on that. But the PDF, it looks like this. So it's unsurprising that it goes to 0 exponentially fast because this function is an exponential function, right? So it goes to 0 exponentially fast. And it turns out if alpha is really, really big, then you kind of tend to go to 0 faster, of course. Okay? As you can see, the exponential 4 goes to 0 fast. Exponential 1 tends to have a little bit longer before it goes to 0. But the tail is very, very thin. We say that. Anyway, so x has an exponential distribution with parameter alpha, which is strictly positive and finite. Then its expectation is 1 over alpha, and its variance is 1 over alpha squared. Okay, and I'm going to show this result myself. I'm not going to do it. I actually don't like this calculation, which I don't find spectacularly easy to follow, although there's not a very hard calculation to begin with. So let me just show you. So this is an alternative way of doing it. You'll see there's only a few lines of calculation. So here I'm using lambda instead of alpha. It doesn't matter. Okay, so here I'm saying the density function f of x. I didn't put this subscript x in those notes because this is from a different lecture course. So it's lambda e to the minus lambda x. X, of course, is positive. I use this sans serif x for a notation for the support of the random variable. The parameter lambda is positive and finite. So if I want to compute the expectation, that's what I'm talking about now. The expectation of x, remember, is the integral over this support, so that's 0 to infinity, of little x, which is the value of the random variable, x, times lambda e to the minus lambda x, that's the PDF, integrated with respect to x. Okay, so now the challenge is how to compute this integral. And here, the easiest thing to do is use the integration by parts formula. So I'm sure you all did integration by parts before, and probably know it off by heart. That's just a rearrangement of the product rule for differentiation, and you integrate both sides essentially. So the idea is that when you have a product of two functions, what you do, just in case you've forgotten, is you choose one as a value. Let's call this one u, and I call this one dv by dx. And then the formula for the integration by parts is u times dv by dx, u times v, between the limits, minus the integral between 0 to infinity of the derivative of u times v. Okay, so in this case, if I choose u as x, then I get x here. The derivative of x is 1, so I get it here. If I choose this as my dv by dx, then I get v, which is minus e to the minus lambda x, which I get there, minus, to get two minuses, so that's why this get a plus here, e to the minus lambda x. Okay, and now what I have to do, so to compute this one is straightforward, because in the limit as x goes to infinity, this goes to 0, because x gets killed by this exponent. So basically, again, this one goes to 0 much faster than this goes to infinity. So the limit as x goes to infinity, I get 0. If I evaluate this function when x is equal to 0, of course, this is just e to the 0, which is fine, but this is 0. So this contribution of this whole term is 0 to the expectation. Okay, and then I have to compute the integral of e to the minus lambda x. That's equal to minus 1 over lambda e to the minus lambda x, because if you differentiate this function, I get minus lambda times minus 1 over lambda times e to the minus lambda x, which is e to the lambda x, minus lambda x. Okay, and now what I have to do is I have to evaluate this functional at infinity. So when x goes to infinity, this goes to 0. Okay, and when x is 0, I get 1. So I get times 1 over lambda, so I'm going to subtract that. So I get 0 minus 1 minus 1 over lambda, which is 1 over lambda. So that's the expectation. So again, this is just so again, if you've forgotten, if you haven't done integration by parts for a while, this is just use integration by parts formula. And I'm using the approach that as I do, if you don't know the integration by parts formula, I can produce a note with it, but you can ask me if you want. If you have forgotten, I'm sure you know what to do this in A-level maths probably, but if you haven't, I can write down the formula even now if you want, or if you prefer, I'll put it in a PDF file so you can read it. Is that calculation clear, or do you want to do it? Do you want me to do it again? So I get no response. I'm going to assume that you're very happy with the calculation. Let me just do the expectation of x squared, and then we will have a break. So now to compute the variance, remember the variance is the expectation of the square of the random variable minus the square of the expectation. So I have the expectation of this, it's 1 over lambda. So the expectation of x squared, again, it's an integration by parts type thing, because by definition, you integrate between 0 and to infinity, because that's the range of the random variable. The function x squared, that's my random variable here. And I integrate with respect to the PDF, which is lambda e to the minus lambda x. Okay, so now I'm going to do integration by parts again. Okay, now what I'm going to do, so this can be done by integration by parts twice, but kind of we've already done integration by parts once here, so you only need to do it once actually. Given this answer, the second answer is relatively straightforward. So the way we do this, one way to do this is you choose the function u is equal to x squared. The derivative with respect to x dv by dx is like this. Okay, so the derivative of u is 2x. Okay, and the integral of this is minus e to the minus lambda x. Okay, so my integration by parts formula is u x squared times the integral of this, which is minus e to the minus lambda x between 0 to infinity. Minus the derivative of this, which is 2x times, so the integral between 0 to infinity minus 2x times, the integral of this, which is minus e to the minus lambda x. So I get a plus here because I've got the minus from this one. I get 2 over lambda, so the 2 over lambda comes from, well, it's not 2 over lambda, there's no 2 over lambda. This one shouldn't be here actually. Oh, no, that's correct, yes. These lambdas cancel. Sorry, yes, this lambda cancel. So I've taken this lambda out and I've multiplied by lambda. So I get 2, and this is the x, and this is the original PDF. Now the reason I've done it this way is because now this thing is the expectation of x. Okay, so now this part, when if I take the limit as x goes to infinity, again it goes to 0 because this e to the minus lambda x kills the x squared function in the limit as x goes to infinity, and at 0 I'll get 0 because 0 times this is 0. Okay, so I've got 2 over lambda, and then I've got this thing. And remember, I've used the trick 1 over lambda times lambda is 1. Okay, so now this thing is the expectation of x by definition. So I get 2 over lambda times this integral, which I've computed here, is 1 over lambda. So the expectation of x squared is 2 over lambda squared. Okay, so the variance of x is 2 over lambda squared minus 1 over lambda squared, which is 1 over lambda squared. Okay, and so that confirms this result here. Here's using alpha instead of lambda. It's the same result. The expectation of x is 1 over alpha, and the variance of x is 1 over alpha squared. Okay, so with that, we'll take a short break for 5 minutes and resume at 14:52. Sorry. Okay, so let's resume. So just to let you know, we're basically just going to cover this part on exponential distribution. So that's 10 pages of the notes plus this thing. It's basically because I think we're going quite fast, so I would be a bit slower these days. Okay, so just a couple of remarks about this exponential distribution. If you make the substitution alpha is equal to 1 over mu, you can write the PDF as 1 over mu e to the minus x over mu. And in this case, it happens to be that the expectation then is mu and the variance is mu squared. Okay, so if you prefer, I mean, this is a nicer looking expression for the expectation and the variance, but the PDF looks more ugly. Exchangeably, this one, the PDF here looks relatively neat, and the mean and variance look relatively more ugly, but it doesn't matter. It's just a way of specifying the parameter. So typically one specifies it this way. Okay, so before going on to this part, I just want to give some additional examples because I think it's kind of interesting. You're going to start to do some more interesting things. So this is an example. Hopefully, it's a little bit complicated, but hopefully you'll get something out of it. And there's some repetition of some of the notes calculations. So this again is, as I said, it's on this alumnus system. You can read this by yourself afterwards if you want. Let me go through it. So we have an example, and it says that the value of a stock, X, at a given time, has a probability density function when X is strictly positive. So this is an exponential PDF, and in this case, the parameter alpha is 1, okay, and it's 0 otherwise. Okay, so this is our favorite PDF. And we're told the following. So the value in dollars of a financial contract is like this. Okay, so what this is is the expected value of the random variable, the maximum of X minus K and 0. Okay, now this is not just, and K is positive and fixed. Okay, so this is not a made-up example, because actually this thing is called a contract, which is called a European call option. It exists in reality. This model is a bit naive for a stock, but you could conceivably have this model. So this actually is called something called an option, financial option, and this is called the risk-neutral price of the option. Okay, it doesn't matter too much for us. We're learning the exponential distribution, so you don't have to worry yourself too much about this. So now you're told the following. So you have a broker, and he or she wants to sell you the contract, and they're going to sell you it for e to the minus k plus $1. Okay, k is a constant, which I'm told what it is. If I calculate this expectation, would I buy the contract that that broker is asking for? Okay, so what do I want to do? All this question asks you to do is to compute the value of the contract, okay, which is this. The expectation is with respect to this density function, okay, and I want to compare it with the amount the broker is selling it for. So if this amount is less than this, then of course I'll buy it from the broker, because basically the value of the contract is more than this person is selling it to me for. But if this number is less than this, then I wouldn't buy the contract from the broker, because he's asking more than what it's really worth. Okay, or she's asking that. So in order to do this question, I was just going to build up some tools before we go along the way. So first of all, just note that we can compute the CDF, the cumulative distribution function for an exponential random variable. So remember what that is by definition. That's the probability that x is less than or equal to some value little x. Okay, so now I take little x to be in the support of the random variable, so I don't have any funny things to worry about. And that is by definition, the CDF is the integral between 0 to little x. Little x is this value here of the PDF integrated with respect to t. Okay, so the PDF is e to the minus x, so I want to compute the integral of e to the minus t, which is minus e to the minus t. I go between 0 to x. So at x I get minus e to the minus x, and at 0 I get 1, so I get minus 1. So the CDF of an exponential random variable with parameter lambda or alpha equal 1 is 1 minus e to the minus x. Okay, so why am I telling you that? Because I'm going to use that fact in a moment. No, clearly if x is less than or equal to 0, the CDF is 0, because basically the probability that I'm less than or equal to some value which is outside the support and less than my minimal value must be 0. Okay, that's what this statement means. Also, we may remark the following. If I want to find the probability that x is bigger than k, I'm going to use this of course in a moment, that's 1 minus the probability x is less than or equal to k, and I've just computed the probability that x is less than or equal to x, so I just substitute capital K into this formula. So this is 1 minus e to the minus k, so that's equal to e to the minus k. Okay. This is just a statement of two facts, and I'm going to use them in my below calculations because I want to be able to calculate the value of this financial contract. So now what do I want to do? Now I want to calculate the expectation of this random variable. The random variable, and x is exponentially distributed. Okay, so that's what I'm going to do. So now let me think about this. So first of all, let me think about this function. Okay, the function I'm trying to highlight. So this means the maximum of x minus k or 0. Okay, so this function is 0. So if x is equal to k, then these two values are equal. If x is bigger than k, the maximum of x minus k is x minus k, and 0 is x minus k, right? So this function, the maximum of x minus k and 0, is only non-zero if x is greater than or equal to k. Okay, so the expectation of this function is basically equal to the integral between k and infinity of x minus k times the PDF. Okay, so again, the reason being that this function is only non-zero if x is bigger than k, and if it's bigger than if x is bigger than k, I get x minus k. Okay, so that's the only trick. After you understand that point, then computing the value of this contract is not so difficult given these above calculations. Okay, so just one more time, sorry if I'm repeating myself. This contract is worthless if x is less than or equal to k, and if x is k or bigger, I get x minus k. Actually, that's the interpretation of it. So if you've never heard of this before, it's called the European call option, and you can Google that on your phone or whatever, and you can easily find out about that. And this is actually the value of a European call. Okay, but for us, all we want to do, nothing more exotic than compute this integral. Okay, and then we can answer the question. So to compute this integral, okay, so I'll split this into two integrals. Okay, this integral is x times e to the minus x, k in infinity, minus capital K times the integral between k and infinity of e to the minus x. Okay, and now this is not so difficult because this quantity here, what is it? It's the probability that x is greater than or equal to k. Okay, and I've done that, that's e to the minus k. So that's good, that's good. Okay. This one, well, I've already done this thing already. It's by integration by parts. So let's do integration by parts here. So the integration by parts formula I apply. So I let u, my function u, equal to x. The derivative of x with respect to x is 1. I take my function dv by dx as e to the minus x. So the integral of e to the minus x is minus e to the minus x. So this integral here on the left is going to be x times minus e to the minus x integrated between k to infinity minus the integral between k to infinity of 1 times minus e to the minus x. And I've just incorporated that into here. That's this part here. So this minus k integral between k and infinity, that's this part here. And the value 1, that's come from my integration by parts. Okay, and now I'm, like I say, I'm in a good position, right? Because this number here, that's e to the minus k. I've done that already. This number here, so the limit is x goes to infinity. This goes to 0 because x goes to infinity slower than e to the minus x goes to 0. And at k, I get k e to the minus k, but I subtract that. So the value of this thing here is k e to the minus k multiplied by probability x is greater than or equal to k then times 1 minus k. This number is e to the minus k. So in the end, the value of my integral is k e to the minus k plus e to the minus k minus k e to the minus k is e to the minus capital K. Okay? What's the conclusion? The conclusion is that the value of the contract is e to the minus k, but this broker is being very sneaky because he wants to pay you he wants to charge you an extra $1, right? So you say, well, I'm not going to buy the contract because it's not worth that. Okay, so you wouldn't buy the contract from this particular broker who's trying to kind of pull one over your eyes and get the contract, get you to pay him for the contract more than it's worth. Okay, so that was example 1. Example 2, the example 2 is the following. So this is a kind of throwback to the last chapter. So if you remember the last chapter, we were looking at joint PDFs, independence, probabilities of x bigger than y, and so on and so forth, and that's what we're going to do in this example. So this example, what we suppose we define this set z, which is just r plus times r plus. Okay, so this is just the non-negative numbers squared. So this is a value in 0. This is just represents the values which are in 0 to infinity, and so does this one. And we define a joint PDF, which looks like that. Okay, and it looks very familiar because it's basically the product of two exponential densities. Okay, so x and y are in this set z, and lambda is positive. So we're asked to find the marginal PDFs of x and y, and we're asked whether x and y are independent. Okay, now this one is a kind of a little very, very simple one to answer. You don't have to do anything. So the way you normally do this is you'd integrate over all x's and get the marginal PDF of y. Right, but you know that if you integrate this with respect to x, what you're going to get is lambda e to the minus lambda y, because lambda times e to the minus lambda x is a PDF. Similarly, if I want to find the marginal PDF of x, I integrate this function with respect to y. Hopefully I've said that. If I want to find the marginal PDF of y, I integrate with respect to x. So I get lambda e to the minus lambda y comes outside my integral, and I want to integrate lambda e to the minus lambda x, e to the minus lambda x times lambda between 0 to infinity. That's 1. So the marginal PDFs of x and y are just basically these things, like this. And if I multiply these two PDFs together, I get this. So immediately, I can tell you immediately that x and y are a pair of random variables which are independent and identically distributed, and they happen to be exponential lambda random variables. Okay, so that's the first one. The second part asks us to y, so x and y are independent. So now I want to compute the probability that x is bigger than y. Okay, so this is basically almost the same calculation that we have done last week. So the probability that x is greater than y is basically going to be, so I'm going to draw something on the board, and I'm sorry for those people who are not here, but who are watching on video, you can't see this, but it's easier if I draw things on the board. So I'll try and draw it so you can hear me, so that you can see it. So what we want to do, so again, I'll try and draw this big enough, but hope, oh God, I didn't draw anything, I didn't have a pen. Maybe this one works. What I want to do is I want to compute the probability x is bigger than y. So I'm trying to make this big enough that you can read it, but hopefully you all know these things already. So this is the line y equals x. Okay, so again, for those of you who are watching on video, you can't see a thing, but basically I've drawn the y-x axis and the line y is equal to x. Now what do I want to do? I want to compute the probability x is bigger than y. Okay, so basically the region here, so we know y is positive, so we're in this domain, we're in this the upper quadrant of the xy axis. Okay, that's what I've drawn here, and the condition that x is bigger than y is this shaded region here. Right, so this is y must go between 0 and x. So to compute the integral, what I want to do, I draw a line parallel to the y-axis upwards. Okay, and so my region here is y goes between 0 to x, so that's what we've drawn here, and x goes between 0 to infinity, so that's what I've got here. Okay, and so that's the trick that we used last week. Hopefully you can remember it. So I didn't write this graph down, but hopefully you can understand that on this line here. So in here, of course, y is bigger than x, y is less than x, and this is the line y equals x. Okay, so that's where this integration domain has come from. So here I'm integrating y first and then x. If I go x first, what I would do is I'd draw a line parallel to the x-axis, and I would go between y and infinity, and y would go between 0 and infinity. Okay, so that's why I've done it this way. Okay, so now the joint PDF, we know what that is. That's lambda squared e to the minus lambda x times e to the minus lambda y. Okay, so first of all I want to compute this integral with respect to y. Okay, so we know the integral of lambda e to the minus lambda y is minus e to the minus lambda y. Okay, and that goes between 0 and x. Okay, so when I get 0, I get 1, and when I get x, I get minus e to the minus lambda x. And so now I just want to compute is this integral here. Okay, so the first one I do lambda e to the minus lambda x by itself, that's minus e to the minus lambda x. And then I've got lambda e to the minus 2 lambda x, which is integrated to be 1 over 2 e to the minus 2 lambda x. Okay, and then I go between 0 to infinity. So at infinity, of course, I'm going to get that goes to 0, that goes to 0, and I get 0. I get minus minus 1 plus minus minus a half, sorry, which is equal to 1 minus a half, which is a half. Okay, so in this case, the probability x is bigger than y is a half. Okay, so this is just a small example which combines last week's joint PDFs, independence and marginal PDFs, and this week's exponential PDF. Okay, and these are just examples. You can have a read of them again if you like, and if you have questions, please don't hesitate to email me. I think this stuff will not be seen by the other classes, so this you get special. Whether you find this interesting, I don't know, but hopefully you find this example useful to understand some things about the exponential density. Okay, so let's resume back to the notes. So we're just going to look at around 10 pages of the notes. So we may be finished a little bit early today, but that's okay. So this is called the no memory. It's actually called the lack of memory property of the exponential distribution. Okay, so let me just state this theorem, and we can prove this one. It's not so difficult to calculate to prove it. Sorry. So we suppose the following. Suppose x has a probability distribution which is exponential, and the parameter is alpha, which is strictly positive. Okay. Then we're told the following. So we have two positive numbers, s and t, and we want the probability that x, so we are told the following. The probability that x is strictly bigger than s plus t, given that x is bigger than s, is the same as the probability x is bigger than t. Okay, we're going to prove this result, but what does it mean? Hopefully he's written it here. Okay, he hasn't. let's interpret that. Let me just interpret what the theorem means. We'll do the proof afterwards. So what this result means is it means that the exponential distribution doesn't have a memory. That means what an example of what this statement means is the following. Suppose x is the length of a life of a bulb. Now what this statement says on the left-hand side is suppose that the life of the bulb has s. Now I want to know what's the time. I want to know whether the bulb lives now to an extra t units of time. Now what this result says is that that's the same as whether I just consider the bulb today and think about whether it lasts t time units, i.e. it doesn't matter that I survived up till time s and then I want to live t2 units more. That's the same as if I just start living now and I think about whether I survive t units. Okay, let me just read this out. I think it's better to understand the interpretation before the proof. I think we'll get more out of it that way. So again, suppose x is the life length of a bulb. Given that the bulb has lasted s time units, i.e. x is bigger than s, the probability that it will last for the next t time units, s is plus t, is the same as the probability it would last for the first t units as brand new. That's what the result means. Okay. Now, whether that's a reasonable model, that's a different thing. But this result is a property of the exponential distribution, and we're going to reprove the result now. Okay. So we know what it means. I hope you understand what it means, even if the proof becomes less clear. But I think it's not so bad. So what I'm going to do is I'm going to start with this left-hand side, and I'm going to show that it's equal to the right-hand side. Okay. So let's consider this. So I want to compute the left-hand side. That's the probability that the random variable x is bigger than s plus t, given that x is bigger than s. Okay, and we know by definition that's the probability that x is bigger than s plus t and x is bigger than s divided by the probability x is bigger than s. So there's just the probability of a given b is the probability of a and b over the probability of b. Okay, now if you think about the numerator here, if x is bigger than s plus t, then x is bigger than s immediately. So this intersection is just the probability that x is bigger than s plus t. Okay, so again, one more time, if I'm bigger than s plus t, immediately I'm bigger than s. So this intersection is just this one. Okay, and so now what do I want to do? I want to compute the probability that x is bigger than s plus t and the probability x is bigger than s. Well, I know how to do that because I know the probability distribution. So remember now we use the information that the random variable x is an exponential. Okay, so the probability x is bigger than s plus t is the integral between s plus t and infinity of the PDF, which is alpha e to the minus alpha x. And the probability x is bigger than s is the integral between s and infinity, alpha e to the minus alpha x dx. Okay, and we did this calculation pretty much in this example sheet, but let's do it one more time. So the numerator, well, that's minus e to the minus alpha x between s plus t, and the denominator is the same except I go between s and infinity. Okay, so at infinity I'm getting 0, so I don't care about that, and I'm just going to subtract the lower limit. So the lower limit here is e to the minus alpha times s plus t times minus 1, so I get a positive here, and similarly here I get e to the minus alpha s. Okay, and so then this the numerator and the denominator cancels to be e to the minus alpha t. Okay, but what do we know? The probability x is bigger than t, well, you can compute it. Right? We've already done it here, actually. You can just put t in here. But if you prefer, the probability x is bigger than t is the integral between little t and infinity, alpha e to the minus alpha x. This is, of course, we know that this integral of this is minus e to the minus alpha x between t and infinity. And so if infinity is 0, and I get subtracting minus e to the minus alpha t, which is e to the minus alpha t. So this thing which I've shown that the left hand, so remember, what have I done? So what I've shown is that this thing here exactly at the end is equal to e to the minus alpha t, and that's precisely equal to the probability x is bigger than t. Or if you prefer, what we have shown is that this is equal to this. Okay, so there are the two critical steps in this approach. One is that this intersection is just equal to the probability of this. The probability of this intersection is equal to the probability of this, and that you just use the exponential PDF in this calculation. Okay? And that's it. And this is the interpretation. So let's look at some examples. There's not much left to do today, so if you're beginning to feel tired of my voice, it's not going to last for too much longer. So example 1 is to find a CDF. Well, we already did that, but let's do it one more time so that everybody's clear. Okay, doing things twice doesn't hurt, just as long as we are clear. So we want to find the exponential distribution as parameter alpha. In my calculation a moment ago it was lambda. It doesn't make any difference. So we suppose we set the value of little x. That's positive. Okay, so we know by definition the probability that x is less than or equal to x is equal to the CDF. Okay, the probability x is less than or equal to x, well, we've done that already, really. We've just done it on the last slide. That's the integral between 0 to little x of alpha e to the minus alpha t. Remember, t and x are different. The integral of this by now is standard minus e to the minus alpha t. If I differentiate this, I will get this. Okay, and so I evaluate this at x, I'll get minus e to the minus alpha x. At naught, I'll get minus 1, so I'll get a 1 here. Okay, and that's the CDF. Well, we knew that already. Okay, and so of course we know that the probability x is bigger than x is 1 minus this. Okay, and we did this calculation twice, or in fact 3 times on the previous few slides. So this one, which is the one which has the silly wording? Is this one maybe? Yeah, this one. Okay, we'll be careful with example 2. So, well, it's the only example left. So suppose we have failure time t if a system is exponentially distributed with mean of 5 years. So the second statement is a bit unclear. So basically what's happening here is you're going to have 5 systems, and you're going to think about the probability that 2 of those 5 systems are still functioning after 8 years. Okay? So first of all, let's think about this question. So first of all, the expectation of t is 5, so our parameter is 1 upon 5. Remember, the expected value of the exponential is 1 over alpha. Alpha happens to be equal to 1 over the mean, which is 1 over 5. So the failure time is exponentially distributed with parameter 1 over 5. So now the probability of failing, that the failure time being more than 8 years, okay, for a single unit is just the integral between 8 and infinity, 1 over 5 e to the minus. That's an x, not an 8. 8x over 5 dx. So the probability that t is bigger than 8, well, we know the formula here is e to the minus 8 over 5. Okay, that's there. So this is x. Apparently it's about 0.2. But we're not answering our question. So our question is now that we have 5 systems. Now we want to work out whether or not they're still functioning at the end of 8 years. So we now suppose that these systems are going to either succeed or fail after 8 years. And they're going to do that independently. And of course then if they're identically distributed. So the number of systems out of the 5 which still function is going to be can be represented by a binomial random variable. The number of systems are 5, and the success probability that they're functioning is apparently 0.2. You don't have to use 0.2. In fact, you should use e to the minus 8 over 5. So now the probability we want to compute, the probability that at least 2 out of the 5, so we want to compute the probability x is equal to 2. That's the probability 1 minus the probability x is 0, minus the probability x is equal to 1. Okay, so we just have to compute the value of these binomial random variable at 2 values. Okay, example 3, and then that's it. No, one more. Okay, example 3. So example 3 is the following. We suppose the response time of x of a certain online computer terminal has an exponential distribution. I find this. Some of these examples, the words are so long that I begin to fall asleep. But the online computers, this is the elapsed time between the end of an inquiry and the beginning of a system's response to that inquiry. Okay, but basically we're asked the response time is exponentially distributed, and the mean is 5 seconds. Okay, we're asked 2 questions. Find the probability that the response time is at most 10 seconds. Find the probability that the response time is between 5 and 10 seconds. This is pretty trivial for us at this stage. Part A. So the expectation of x is 5. It's just not p. P is a typo again. Sorry, this thing is not working very well. Anyway, so the probability, so the random variable x is exponential with 1 over 5. So again, this is a typo. There's no p here. So the answer to part A, we want to find the probability the response time is at most 10 seconds. So I want to compute the probability that x is less than or equal to 10. Well, we know that already, right? That's 1 minus x, e to the minus lambda x. Okay, lambda is 1 upon 5 here. So that's 1 minus e to the minus 10, which is x, times over 5, which is lambda. And that's 1 minus e to the minus 2. Okay? And for me, you can stop here. This is a precise solution to the question. You don't have to write the decimals out. I would never dot marks for that. Part B, find the probability the response time is between 5 and 10 seconds. This is straightforward again. That's just the probability that x is less than or equal to 10 minus the probability x is less than or equal to 5. Okay, the probability x is less than or equal to 10 is 1 minus e to the minus x, which is 10 times lambda, which is 1 upon 5. The probability x is less than or equal to 5 is 1 minus e to the minus x, which is 5 over multiplied by lambda, which is 1 upon 5. So this just becomes, at the end, this one's e to the minus 1 minus e to the minus 2. And you can stop there. That's the solution. Okay, if you want, you can put the number into your calculator. Okay, so let's just to finish off this today's lecture. It's a little bit early, but I think that's fine. I don't want to get too because I don't want to get too far ahead. Actually, I think we're well ahead of the other two groups, so at least we will slow down a bit. So this is an application. So you saw one application before. That was the model of a value of a stock. It's a bit I mean, you can use exponentials, and generally you use something else, which is called log normal, but we'll talk about that later on. The main application actually is this exponential distribution plays a role in this Poisson experiment. So if you remember at the end of last week's lecture, I was talking about this Poisson experiment where the chance of two events occurring in small interval is small and so on and so forth. This is actually the time between inter-events. This distribution can be derived explicitly as the distribution of the time between events in a Poisson experiment. Actually, but we don't do that because we don't study the Poisson process. But it's used as times between occurrences of successive events. That's exactly where it comes from, such as customers arriving at a service facility or calls coming into a switchboard. So there are many applications of the exponential. In fact, after the uniform distribution, unsurprisingly, it's the most basic distribution that one would use for continuous random variables. Okay, so that's pretty much all I wanted to talk about. I'm happy to talk about the rest of this, but that'll give us something more interesting to look forward to tomorrow. And we're going to talk about the Gaussian or normal distribution, which I'm sure you've all heard of already. So thanks very much for your attention, and I'll see you tomorrow's lecture. Thanks.